Swayam Prabha. Digital India. Educated India.
So now we come across LU decomposition. Based on we have to discuss LDL transpose factorization. Now we have a theorem. Every real symmetric positive definite matrix can be factored as LL transpose, where L is a real lower triangular matrices having positive elements on its diagonal. Now you have to refer Golub and Van Loon in the year of 1996 published the page of LDL transpose factorization. Under certain condition we can find the Cholesky LL transformation factorization directly from LU factorization. Suppose we are given a real symmetric positive definite matrix A and its factorization A equal to LU, where L is the unit lower triangular matrix and U is the upper triangular matrix with the positive diagonal elements. We can extract the diagonal elements from the matrix U and use them to form a diagonal matrix D, so that A equal to LD L transpose. Then we can split the matrix D equal to root D into root D, because the diagonal matrix D has a positive diagonal elements. So we obtain where L equal to L D power 3 by 2, that is A equal to LD power of and D power of into L transpose, which is equal to LL transpose, where L stands for L D power of. So keep it in mind this. So LD L transpose factorization we can understand. Now we are going to discuss one example. Now carry out the process of just to describe the following matrix A equal to 6, 3, 4, 4 and 5, 3, 2, 1. Now first to carry out the forward elimination phase of the Gaussian elimination technique, that is leading diagonal 6 and below leading diagonal we have to make a 0, that is this is R1, R2, R3. So R2 such that 2 times of R1, 2 times of R2 minus R1 you do that, so that it will come 0 of minus 1, and similarly the fourth equation 6 times by 4 and then subtract with R1 we have what 0 minus 1 7 by 3 will come, and further we have to reduce this element to 0 and making use of what that is third row divided by half and then simply add them, you can get the third row. So that the row reduced matrix 6, 3, 4, 0 of minus 1, 0, 0, 1 by 3 will come. And using this A and we can split it into what the LU, that is 1, 0, 0 of 1, 0, 2 by 3 minus 2, 1, which is equal to what 6, 3, 4, 0 of minus 1, 0, 0, 1 by 3. So this is the meaning of lower triangular into upper triangular, and this can be further splitted into LD L transpose. L you know, and then U you know, L you have to find the inverse, so that determinant of L you have to find out, the inverse is L transpose determinant U. So L you know, L transpose simply transpose to the first matrix, so that this matrix will come, and keep this matrix as it is and this matrix as it is. Now normal matrix multiplication you do that, so this matrix will come, and this is 3 cross 3, also this is 3 cross 3. You have to multiply them and you may get what LL transpose technique. So evidently we have found LU factorization and LDL transpose factorization of LL transpose factorization technique can be easily evaluated. next to QR factorization. The vector x is a least square solution of the system of equations. Now, Ax equal to b under the circumstances just described. So, we have a proof, compute A transpose into Ax minus b, which is equal to what, that is QR. A is nothing but q into r whole transpose. So, QRx minus b. You know QR of whole transpose is nothing but R transpose into Q transpose, and then this can be written as R transpose into Q transpose, and QRx right here, and B is nothing but R transpose Q transpose B, because this is multiplied with the B. Now, combine together associative property R transpose into, this is Q transpose into Q is I. Therefore, R transpose into Rx will come, here it will generate like this. Now, R transpose, the Rx is Q transpose B, and this keep as it is, so that these two are equal, it becomes 0. So, consequently, the normal equations are satisfied, implies from this equation A transpose of Ax minus B equal to 0. So, A transpose Ax minus A transpose B equal to 0. So, this is the required value of what? The QR factorization. Now, we have a theorem. You take a M cross N matrix of rank A as a QR factorization, where Q is M cross N matrix and Q transpose Q is I, and R is a N cross N upper triangular matrix which is invertible. So, for example, QR factorization of the matrix A equal to 1 2 1 0 1 2 1 0. So, by applying the what theorem, so by step with the process of the Gram-Smith process of normalization, first column A1, this Q1 equal to 1 by 2 1 by 2 1 by 2 will come, and next we subtract from the second column A2 with the projection on Q1 already we discussed, and refer V equal to A2 minus of inner product A2 Q1 into Q1, which is equal to A2 minus 2 Q1 will come, and corresponding the values is 1 minus 1 1 minus 1. After normalization, Q2 will generated, and our work gives us A1 equal to 2 Q1 and A2 equal to 2 Q1 plus 2 Q2. So, this equation implies R11 R12 equal to R22 are equal to 2 and R22 is 0. Hence, we obtain the matrix corresponding to Q1 Q2 generated, and we can convert this to this, and then if these two matrix multiply with what corresponding entry of 2 2 0 2, so that Q1 Q2 into R is QR will be generated. So, this is a technique of QR decomposition. So, based on this SVD also works. So, any matrix can be put into factor of PDQ, where P and Q are unitary matrix and D is a diagonal also holds good. Now, we have a Skerr decomposition. Let A equal to C of a N cross N matrix. There exists a unitary matrix U belongs to N cross N matrix. So, A can be written as U T U H, and the eigenvalues of A appear on the diagonal of the upper triangular matrix. So, according to the corollary, A belongs to N cross N Hermitian matrix. Then there exists a Hermitian matrix U in C of N cross N. So, A equal to U D H, where eigenvalues appear in the diagonal matrix T. If A belongs to N cross N matrix, there exists a invertible matrix S in R power N cross N, and a triangular matrix T such that A equal to ST S inverse and the eigenvalues of A appear on the diagonal of T. So, these are all the further analysis with the help of the Skerr decomposition. So, we have to discuss some simple example, then we will go to the depth of the Skerr decomposition. So, we have to illustrate with the Skerr with some example of 2 cross 2. So, A equal to 5 minus 2 7 minus 4, find eigenvalue. So, A minus lambda I, find the determinant. So, after a determinant we have the characteristic equation lambda square minus lambda equal to 6 equal to 0 and factor it. So, lambda equal to minus 2 and 3 are the roots. If A minus lambda I equal to 0, then the corresponding eigenvector V1 equal to minus 1 and 1 and V2 is 7 comma minus 2. So, using Gram-Smith orthogonalization process of eigenvalue eigenvector, we obtain U1 and V1 and we can easily calculate U2. After normalizing, we have U vector will come 1 by root 2 into minus 1 1 1. So, after getting U and UH transpose, you have to calculate. Finally, we have a Skerr decomposition of the matrix will be generated. So, this is the upper triangular matrix having eigenvalues on the diagonals. So, this is the verification we can do with the help of that step. Now, we go to the depth of the Skerr decomposition. The Skerr, for taken a theorem, the Skerr decomposition for any n cross n matrix A which entries from C, there is some orthonormal basis B of C and upper triangular matrix B R. So, the entries are A equal to B1 B2 and so on Bn R into B1 B2 Bn inverse. So, in other words, you take n cross n complex valued matrix, there is an orthonormal basis in which matrix is upper triangular. So, we prove this theorem, we provide an example of such a decomposition and finally use this decomposition. Calculating something would be, otherwise it would be far difficult. So, the proof is number 1, to proceed in 4 stages. First, find eigenvalues lambda 1 of A. So, we are guaranteed that some such a lambda 1 exists by our earlier result. Number 2, P suffix lambda denote the set of all vectors V such that AV equal to lambda V. This is the subspace of C. So, the linear combination of vectors in the space are still in this space, therefore, it has a orthonormal basis and pick some orthonormal basis of B1 lambda 1 and so on Bk lambda 1 for this space. Third one, we extend the basis to an orthonormal basis for all Cn. This is easy to do one by one. Pick a vector not in the span of our basis and run by Gram-Smith process to make a orthogonal to everything in our basis. And this new orthogonal vector Ci to our basis. So, until we have n vectors in our basis, at which the point will have a orthonormal basis for Cn. And fourth point, write our matrix A in the orthonormal basis B1 lambda 1 bar, Bk lambda 1 bar and so on Cn bar Cn minus k bar. So, what does this look like? Well, we know that for each Bi lambda I, by definition, we have A Bi lambda 1 equal to lambda 1 Bi lambda 1 bar, which is our orthonormal basis in which the vector of the ith entry lambda 1 and the rest 0. In other words, we know the first k columns of our matrix. In particular, our matrix has the following form. So, this have a eigenvalue and this has a remaining of the letter and below the diagonal 0 and corresponding A2 will come. We have n minus k1 entry. So, to be specific, the above matrix consists of 4 distinct blocks. First one is k1 cross k1 diagonal matrix of upper left, lambda is on its diagonal and else other place is 0. And B is n minus k1 cross k1 matrix, the lower left mad entry of zeros, and then the third one k1 cross n minus k1 matrix of the upper right corner, which name A or EM, and the fourth one is A2 is n minus k1 into n minus k1 matrix in the lower right corner, we call it as A2. Now, the fifth point, consider the matrix A2 according to the definition, a linear map that takes its vector from the span of the vector C1 to Cnk and outputs vector within the same span, and in particular A2 is now the square matrix over some vector space, and put back to the steps 1 to 4. We can do this whenever this matrix A2 exists, so which is n minus k1 in non-zero. So, what we do now, we have an orthonormal basis b1 lambda 1 bar, b and so on, bk1 lambda 1 bar and so on, cn minus k2 minus k2. So, shown that the matrix A under the above basis has the form AB, A suffix B is first, this one is a eigenvalue and k2 entries of A or EM, and n minus k of minus k2 entries like that. This is the k1 entries, and for second set is 0, put it and start with lambda 2 to lambda 2, and A remember k2 entries, and the rest of them is 0 of the below diagonal, and n minus k1 minus k2 entries like that. In generalized form of the matrix we can do that. Now, do it again to A3 and keep repeating this process until we cannot continue. So, what does our matrix under our resulting look like then? Well, we have filled its diagonal elements in the main matrices which have only zeros below, and other matrices is upper triangle. So, why we care the square decomposition? The above decomposition is incredibly useful in certain situation like raising the matrix to some large power, and we have to study some example like consider the matrix A equal to 13, 8, 8, minus 1, 7, minus 2, minus 1, minus 2, 7. How to calculate A per 50? So, that is the speciality of square decomposition. Now, we have a proof. Let us start with directly computing time and power. So, this seems to be very bad. Therefore, how can we do the faster? Well, we might hope to get for using the UD inverse, where D is a diagonal matrix and U is upper triangle matrix, and the corresponding inverse you find out, and no pair of the matrices U and D such that U is invertible. Therefore, A equal to UD U inverse. So, we can do something good for that, finding the A square decomposition, and we talk about the useful for finding A per 50. So, it is very difficult for normal. Therefore, and this technique will be very helpful to attack the problem of finding the rising to the power of any number. So, to find the eigenvalue with corresponding non-trivial eigenvector of A, so we have the vector x comma y as a constant lambda, that is given matrix 13, 8, 8, minus 1, 7, minus 2, minus 1, minus 2, 7, multiply with x, y, z, so that what? The matrix multiplication is 13x plus 8y plus 8z minus x plus 7y minus 2z minus x minus 2y plus 7z equal to, you call it as lambda of x comma y comma z. Now, we have a basically shouting try to setting lambda equal to 9, and it satisfies our equation. So, 3 of our equations simplify the same constraint with x plus 2i plus 2z equal to 0. Now, we have a idea to come into the mind of getting the values 2 minus 2, 1, and checking the corresponding eigenvalue x values, right, is x equal to 2, y equal to minus 2 and z equal to 1, and choose the eigenvalue as 9, and corresponding values of this one will get 18 minus 18, 9 will come. So, multiply with this. So, this is a technique we can use it. So, we have a eigenvalue. Now, for the Skerr decomposition, the eigenvector is corresponding to eigenvalue is x plus 2i plus 2z equal to 0. So, we check it out the orthonormal basis for the space and find the basis, and the basis is 2, 2, minus 1, 1 already we taken, and immediately we have a what some other vectors of 0, 1, minus 1, and then it satisfies the constraint of x plus 2i plus 2z equal to 0. So, according to Gram-Smith process, taken as a u1 bar equal to 2 minus 2 1, and based on the u1 we can calculate generate u2 bar. So, you know the formula for u2 bar of the Gram-Smith orthogonalization process. So, u2 bar minus projection of u2 by norm u2, so that we have a inner product of u1 into u2 by what norm u2 square into u2. So, 0, 1, minus 1, and then the inner product you have to do that, and norm you find out and simplify. You have 0, 1, minus 1, and then dot product we have 3 by 9 into 2 minus 2 1, and then corresponding entry add, so that 2 by 3, 1 by 3, minus 2 by 3. So, we scale this vector and E9 will get what, that is 2 by 3, minus 2 by 3, 1 by 3, and 2 by 3, 1 by 3, minus 2 by 3. So, previously we evaluated. Now, we can extend it to the basis for all C cube, and we take some vector not span of these two E vectors like 0, 0, 1. So, why this is not in their span? Because perform the Gram-Smith on the third vector. So, u3 equal to what we have taken the vectors 0, 0, 1, and the projection of these two already 0, 0, 1, and you take u1 minus projection of 0, 0, 1 onto u2 vector, and using the Gram-Smith third generator of 0, 0, 1 and dot product of these two and divided by norm of this vector will be 1 by 3 by 1 into this, and this is 2 by 3 by 1 into this will come. Simply add the corresponding entries, so we can get u3 equal to 2 by 9, 4 by 9 and 4 by 9. Now, scaling this vector by its length, and then we have a root of 36 by 81 equal to 2 by 3 will come, and this gives as the corresponding vector 1 by 3, 2 by 3, 2 by 3. So, we have a orthonormal basis B1 lambda, B2 lambda, and C will get it. Now, we need to write our matrix A in the basis, and to do simple note that because B1 lambda and B2 lambda are both eigenvectors of the and eigenvalue lambda equal to 9, and exactly where A sends these vectors, and specifically AB1 lambda equal to 9B1 lambda, and we have a basis vector 9, 0, 0. Similarly, AB2 lambda equal to 9B2 lambda, we have another basis vector. So, as per the Skerr technique, we have the given matrix into this set of vectors of a C vector, multiply them, and this is 3 cross 3 and 3 cross 1. So, we have a 3 cross 1. So, 15 3 will come, 15 3 3 will come, and based on that you have to 9 B1 lambda, 9 into B1 lambda is 2 by 3 minus 2 by 3 and 1 by 3, multiply them, we have a what 999 B will come. Therefore, our matrix A on the basis have a diagonal 999 and 099 will be written in the form of what, AB. So, in other words, under the orthonormal basis we have found A is upper triangular, and we have the Skur process to get upper triangle matrix, and the lower right angle block was bigger. If we were look at a 4 cross 4 matrices, and we might have had to repeat the process, and so we use the rise A to be larger power. Well, notice that if we write AB whole power 50 equal to what? The diagonal matrix into this matrix 999 and above and below diagonal 0, and rest of the entry do that, and taking the power 50 is very simple now. So, we can easily calculate A power 50. So, any matrix of the powers can be generated with the help of the Skur decomposition, and then the 9000909 whole power 50 plus and 50 C1 into the rule in the binomial expansion, and then do that. So, this is A power m. So, 50 C1 into A power 50 49 into B, and 50 C2 into A power 50 minus 2 into B, like that. So, we have to expand 50 C 50 so that this matrix will come. I hope you can easily develop what the all values, and only values of 0, 0, 9, 0, 0, 9, 9, 0, 0 whole power 2, and the rest of them all zeros matrix. And we can easily simplify, in particular the term 0, 0, 9, 0, 0, 9, 0, 0, 9 whole power k is a generalized form if k is equal to 2 and above is holds good. So, that is the most advantage in the Skur decomposition. And then AB A suffix b power 50 can be generated like this with the help of the binomial. So, 900090009 whole power 50 plus 50 C1 into 900099009 whole power 49 into this matrix, and go ahead till 50 C, that is these two terms only will be generated, rest of them will be 0, and then this term and this term will come, and this can be easily calculated 9 power 49 and 550 into 9 power 49, 550 9 power 49, and rest of them like this. And then this is the corresponding value of 9 power 50 0 0 0 9 power 50 0 0 0 9 power 50, and this value we have multiply them, it becomes 0 of first column, second column also 0, third column only we have the value 50 into 9 power 50, 50 into 9 power 0, and then add the corresponding entry. We have 9 power 50 0, 50 into 9 power 50 0, 9 power 50, 50 into 9 power 50 0 0 9 power 50. So, this way we can calculate the power of 50 of the given matrix. So, if we convert back to the standard basis, we have A and U, and then using the Skur we have A power 50 and then U transpose, and multiply them, you have the matrix A has a 9 power 49 to normal matrix multiplication, do that, you get the value. So, wonderful answer, we can easily get it with the help of this Skur decomposition, and so it is easily calculated with the help of this technique. Now, the people actually find it the Skur decomposition. So, do not use repeated Gram-Smith to find the Skur decomposition. Instead, they use the following absolutely beautiful application of QR decomposition to find the Skur decomposition. So, the theorem takes that some n cross n matrix with entries in C. Suppose A has a n distinct eigenvalues. So, the Scarred decomposition is QS transpose RS QS. Consider the following process. Set A1 equal to A and find the QR decomposition of Q1 R1 of A. Define A2 equal to R1 Q1. Now, find the QR decomposition Q2 R2 of A2 and repeat the process, and AK as a QR decomposition of QK RK, and we have a suffix k plus 1 equal to RK into QK. So, we notice that A suffix k plus 1 equal to RK into QK. So, RK QK is AK plus 1 and substituted, and this becomes QK transpose into QK RK QK, and then it becomes identity and they reciprocate it, and QK RK is the basis of this. So, the eigenvalues of A and A cluster do not change. Further, the following very surprising fact holds good. If you have a sequence A1, A2 and so on, the diagonal of the matrix coverage converges to the eigenvalues of A factorial. In fact, in many situations, we actually having something stronger. So, the sequence of AIs will converges to RS, the sequence of AIs will converge to RS. So, the upper triangular part of the Scarred decomposition, in other words, we have a limit of AN is RS. Therefore, the proof is beyond this course. Therefore, cool to know the theorem nonetheless. Now, this gives the 3 linear equation which we can solve with 13x plus 8y plus 8z equal to lambda x. So, minus x plus 7y plus minus 2z equal to lambda y, minus x minus 2y plus 7z equal to lambda z. So, in particular, 4 copies of the second of the first gives as, so 9x plus 36y equal to lambda x plus 4 lambda y if and only if 9 minus lambda into x equal to 4 lambda minus 36 into y. Similarly, adding the 4 copies of the third to the first, we have 9 minus lambda x into 4 lambda minus 36 to z will come, and subtracting third from the second, we have 9 minus lambda y equal to 9 minus lambda into z. Next, a small problem with the help of the Hermitian matrices. Suppose A equal to 3,